Swayam Prabha. Digital India. Educated India.
So, in the last lecture we looked at bus bar differential protection. Today we will look at transformer protection. Transformers, as you know, are actually devices which made AC transmission possible. In fact, the very first transformer was a Scott connected transformer. The first generator transformer was a Scott connected transformer, 2.2 to 22 kV, and then 22 to and then 11 to 2.2 on the consumer side. So, since then the transformation ratios, the number of transformers have grown exponentially, and today in a typical network we have the transformation capacity is about 5 times that of the generation capacity. So, the number of transformers etc. could be about 4 to 5 times that of the generators. So, it is a very important network element. The ratings also could be very high, and since it is important for service continuity, it also is an important element which needs to be protected. So, for transformer protection, basically we will look at 3 broad categories. We will of course there are others also, there are mechanical type of protection, that where you have oil temperature, winding temperature, then you have Buchholz where basically operates on gas, but we are not looking at that today. We will look at primarily at differential protection and then just have a cursory look at over-excitation protection also. Okay, so we start our lecture on transformer protection. Okay, so basically we are looking at 3 types of faults. One is the internal fault. So, this is best handled by especially for larger transformers, is best handled by differential protection. Okay. The second type could be, of course, this is not exactly classified as a fault, but there could be overloading on the transformer. Also, another cause of overcurrents. Overloading is basically loading the transformer beyond its current rating. Another cause of overcurrents could be external faults. Okay, now differential protection will not, because there is no internal fault. So, the current entering, we will see it very shortly, but the current entering the differential sort of element and leaving will be the same. So, that is why these faults will not be picked up on differential protection. Of course, there could be mal-operation if the currents are too high and one of the CT saturates, but we are not looking at that right now. So, but that is a mal-operation, that is not protection provided by the differential relay. So, for this the thing is you could provide it with instantaneous overcurrent protection and other means, also overcurrent protection, which we have seen in the earlier classes. The third type is which could lead to damage in the transformer is over-excitation. Okay, so over-excitation is basically transformers are, as you know, are operated very near to the knee point of the material for greater efficiency. So, if the flux increases in the transformer, then there is a chance that the core might saturate, which also leads to an increase in eddy currents. With the result that there could be heating and damage and subsequent damage to the transformer. Okay. So, now first we will then the most important part, the smaller transformers of course can be protected by overcurrent relaying itself, but above a certain size of transformer, usually about 10 MVA in most networks, differential protection is also provided. So, we did look at principles of differential protection in the early part of the course, but also we looked at it last time when we saw bus bar differential, but we will quickly have a look at the principles again, so that we can refresh our memory, and this becomes a standalone lecture in that sense. So, we are not talking of now transformers in particular. We will look at an example of a transformer in this class of course, but we are just talking of some network element. Okay, could be transformer, could be motor, could be generator, anything. So, this is that network element, whatever it is, say some element E, which needs to be protected with using differential protection. So, we have the CTs on both sides to measure the currents. The convention of course is we will use the dot convention, and the current which is entering the dot will also leave the dot on the other end. So, this is the normal flow of currents. Of course, if there is a fault, then the current will reverse, but now we are talking of normal operation only. So, that's then we will connect these CTs. This is of course only a representation. So, we are drawing only one phase. We will look at a 3-phase transformer a little later, okay, because we are just discussing the principles. So, single phase is sufficient, and then you can then extend the principle to multiple phases and even multiple. This is a 2-terminal equipment, you can extend it to multiple circuits also, maybe a 3-terminal equipment and so on. Okay. So, now the current, as we said, as per the dot convention, this will be the you can have the dot here. So, current this dot, the current will leave the circuit. Okay. So, this will be the flow of current. Now, here if you okay, now what will be this current? This is the primary current of the CT. Now, we are not just for the moment do not think of this as a transformer, some element. So, this is IP minus say I dash, okay, which is equal to IR dash, and this is IP minus I. These are the excitation currents of the two current transformers, okay, IE dash and IE double dash. Okay. Okay. Actually, I will not write it as this, I will just say that these are the currents flowing here. Okay. Now, what is the operating current? This is the I am sorry. This is a sensitive overcurrent relay here, and this can be called as the operating current. Okay. So, the CT ratios etc. are adequately matched, the operating current will be only the difference in the difference in the excitation currents, which is normally very small, and hence there is no hence I am sorry hence there is no operation of the relay, and hence for normal operation or for external faults this relay will not operate. Now of course the issue is that there could be CT ratio, I mean the CT ratios are not exact, so these IPs may not be matched evenly. Also there could be a slight difference in the excitation currents. Also for through faults the difference itself may be very large. So what is done is there is a restraint provided, okay, for to make it if you want to make this this relay to be very sensitive in terms of operation, then what we will have to do is if you want to prevent it nuisance tripping on even small differences, then you have to provide some kind of restraint. So a restraint winding or a restraint coil is provided, and what that does is I will just show you this here. Okay, this is the operating coil. This is actually this part. This is actually this part here. Okay, this T junction here. Okay, and then there is one restraint current which is IR dash, and this is IR double dash, which is nothing but these two currents, IR dash and IR double dash. Okay, so so what you have is the restraint current is plotted on the this is either now this depending on the design of the relay, it is either IR dash or a smaller of the two, or IR double dash, or even a average of the two. Okay, it could be IR plus IR dash plus IR double dash upon 2, and this is I operating. Okay, and then you could have a restraint region. Restraint for operation and operate. How the slope and all that is set we will come to very shortly. Okay, so this is what happens. You in normal conditions this IR and IR will be like this. If there is an internal fault, this could reverse. So the restraint goes down significantly, or it could even be 0. Okay, so that is why the operating region will now shift to the operate zone and the relay will operate. Okay, so this is the normal how the normal current flow looks like in these operate and restraint coils. But if there is a fault, then IR dash will be like this, and IR double dash will be like this. I operate will be significantly higher because of this current, since the directions are reversed by Kirchhoff's law, it will have to flow through this, and since the directions have reversed, if you take an average here, the I restraint will also reduce. So the relay will operate. Okay, so this is the overall theory for the differential operation. Now there are a few challenges with transformers. And what are those? One is that the primary of the transformer carries the no load or excitation current. Okay. Second is of course common too, but even more sort of significant in terms of transformers is that the transformer will have a certain ratio, and the CT ratios on the either side cannot be exactly matched, or it might not be possible, right? Rather than saying cannot be, it may be possible in certain sorry situations, but CT ratios sorry might not be exactly matched. And the third of course is another problem which is unique to transformers is there could be taps. Now these could be taps could be in phase taps for voltage control, okay, or it could be quadrature taps also, phase shifting transformers, etc. These are not very common. There are very specialized transformers for this, and nowadays this can be achieved with power electronic devices also. Not very common, though they are certainly used. But voltage taps online, whether on load or off load, are certainly in wide usage. Most power transformers will have taps. Okay. So to take care of these, we use what is known as a percentage biased relay. Percentage biased differential relay. Okay. So in this the earlier diagram, how these characteristics look like is that the slope could be made variable. Okay, if this is the restraint current IR dash or IR dash plus IR double dash by average of the two, and this is the operating current or the differential current, and then this you could have variable slope characteristics. Okay, so this is 10%, then you may have a 25%, 40, and say 50. Okay. You could also have something known as variable restraint. Okay. This is fixed restraint, you could have something known as variable restraint. Okay. Now typically for transformers, this is the percentage characteristics are which are set are typical. I am not is about 15% to 60%. Okay, so this will provide for provides for or takes care of CT ratios, excitation, taps, okay, and types also. Okay, so so what does this imply? Say, what does a 50% tap imply? So for an external through fault current of say 50% tap, okay, just as an example, 50% tap implies that for an external through fault means not in the equipment, current of 10 amps, the operating current will be 5 amps. Okay, that is what a 50% characteristic implies. So, of course, now over time the relays have evolved, and larger and larger transformers were included in the protection. So, the following features were provided. Okay, the first was, of course, harmonic restraint, because we will look at this in detail because this is important. So, this is the second harmonic restraint. Now, this is for inrush currents. When the transformer is first energized, or if there is a temporary dip, or if there is a parallel transformer which is energized, then there could be an inrush current in the transformer. So, this and this inrush will look like a fault, because there is no equivalent current on the secondary side for the CT, for the secondary restraint. So, this will look like a fault, and the differential relay could operate. So, to avoid that, a restraint based on the second harmonic is provided. There is also another restraint which is provided, is fifth harmonic restraint. Okay, now this is to take care of excitation. Excitation current, I have not written it, but it implies that it is meant to take care of excitation current. Now, the excitation current has about 11% of fifth harmonic. So, if we could provide a restraint based on that, third harmonic is also present, by the way, which is about 26%. But the problem with the third harmonic is, if there is a delta connected transformer, then you may not have enough, it may flow only in the inside the windings of the delta, and you may not you may not sense it to provide restraint. So, it is better to provide fifth harmonic restraint. Okay. So, so this is provided, and instead of a fixed restraint or a fixed percentage differential bias differential characteristic, you provide a variable, because this is because to take care of, or rather because the CT, for a large through fault current, the CT could saturate. So, to avoid that, when rather when it is small, the and the CTs have not saturated, you could have a smaller restraint. But when the current increases substantially, or say an order of magnitude or something large, then the one side could go into saturation or partial saturation. To take care of that, you provide a larger restraint. So, then you have a variable kind of restraint. Though this shows a continuously variable restraint, you could also have, I will just draw that characteristic, variable percentage differential characteristic. So, what we were saying is, though the in actual practice restraint and operate or differential. Okay, now this could be, this could be either like this, or you could have number of slopes here. Okay, so with, in fact, with numerical relays, a lot of possibilities exist. Okay, so now, of course, this is to take care of CT saturation. Since I have written reasons for the two of them, I would write. Okay. So, now we will one very important issue that that we have to take care of is the inrush current. Okay. So, we will have a look at it from a circuit viewpoint, and then I will also explain from a phasor kind of or rather the sinusoids, what happens actually say this is a transformer with which is energized at t is equal to 0. Okay. So, open circuited transformer energized at t is equal to 0. Now, according to Faraday's law, you will have Vm sin omega t is equal to d lambda by dt. Okay. So, where lambda is a total flux linkages, which is, say, this is N1 is to N2. Okay. So, and this is Vm sin omega t. So, this is N1 into phi m. Say phi m is the maximum value of the flux in the transformer. Okay. So, now if we just integrate this these two sides, say 0 to t up to t, what happens? D lambda is equal to integral Vm by omega. I am taking, you will soon see why, sin omega t d t 0 to t. Okay. So, you will get lambda of t minus lambda of 0 is equal to Vm by one minus cos of omega t. This is correct. Okay. So, if I were to write it in terms of the flux, then I will get phi of t minus phi of 0 is equal to, oh sorry, I missed omega here, Vm by n1 omega 1 minus cos of omega t. Okay, and then phi of t is Vm by n1 omega 1 minus cos of omega t plus phi naught. Now, what would be the maximum value of this flux? Maximum value will occur if, say, cos of omega t. So, it will be 2 Vm by, okay. So, it can go to 2 times the value of the sinusoidal flux. Now, how does that happen? Say, and we are taking phi naught equal to 0. So, there is no residual flux in the transformer. Okay. So, say the transformer is energized at t is equal to 0. This is the Vm sin omega t waveform. Okay. So, this is Vm, this is t. Now, normally what would have happened is, due to the highly inductive nature, the transformer X by R ratio is very high. So, the normal flux wave would have been like this, maximum here, 0 where the voltage is maximum and so on. But now, since you are and there is no phi naught, and since you have energized we have energized the transformer here, what happens is the flux has to start here and reach this value 2 phi m. Say if this was phi m, then this will become 2 phi m. Okay. So, something like this. Okay. Because it has to reach from to reach a value of 2 phi m. Okay. And to achieve this flux, the corresponding excitation current will also be very high. Okay, something of this nature. Okay. So, of course, and then it depends on what the remnant or residual flux is also. So, it could, if that is positive, then the total flux will even increase even further. So, it will become phi m by phi r. On the other hand, if it is negative, then it will be 2 phi m minus phi r. Okay. So, now as we said, this can happen in 2 or 3 cases rather. One is, of course, when initially the transformer is energized, initial energization. Two is there could be a temporary dip due to faults. If there is a three-phase fault, say just after the transformer, and that is cleared, so that though the voltage will recover from almost 0 to back to normal voltage, and that is known as a recovery inrush. It may not be as bad as the initial inrush, but it is there all the same. And the third one is of course a sympathetic. Sorry, got the spelling wrong. Sympathetic inrush. This happens when a parallel, usually happens when a parallel transformer is energized. So the inrush there will cause a similar inrush here. So it is known as a sympathetic inrush. We are not going into details of all this. We are just as protection engineers, because we are not studying this inrush phenomenon here, but as we should be aware that what are the kinds of inrush and what kind of restraint is provided. The next is then we will move on to the next, which is the overexcitation protection. We will look at an example of transformer differential and how it is set very shortly, but before that let us complete the overexcitation, because overcurrent we have studied. Now that will leave only overexcitation protection. Okay. So now what is this overexcitation? You know the flux, the flux is related to the voltage by the equation, famous transformer equation, Vm or Em is equal to 4.445 N or N1 and F. So F I would write here. Okay. So now what does this imply? That phi is proportional to V by F. Okay. So what if there is some and this is very common with transformers in large networks or transmission networks, is this if due to some reason this voltage were to increase and say the frequency also were to reduce, then the flux would flux in the transformer would increase. Okay. So and as we have already discussed, this because the transformers are operated very close to saturation due to reasons of efficiency, this could lead to saturation of the transformer cores, leading to a heating and other which could damage the insulation, the oil, etc. So to avoid this, there are what are known as volts per hertz, which is, the name is okay, and these relays are provided for protection against overexcitation. If the value exceeds a certain threshold, if the V by F exceeds a certain threshold, this relay will issue a trip command. Okay. So now this, for complete protection you will provide differential relays, overcurrent relays of course for through faults, and overcurrent means mainly instantaneous relays, and then you will provide an overexcitation relay. Now finally we will study application of differential relays to transformers, because transformers is a slightly, I won't say complicated, but we have to take care of a few nuances. Okay. So we will do that with an example. Okay. So the one of the basic principles is we will have to provide restraints for all the circuits. For all circuits, meaning if it is a 2-winding transformer, then 2 restraint windings, coils or windings, whatever you whatever is the terminology you would prefer to use. So there are 2-3 fundamental principles that we need to keep in mind. One is use a restraint winding for all sources of fault current. So, if there is a 2 winding transformer, use 2, for 3 winding you use 3, up to 6 restraint windings are available. Okay. So, the second one is avoid paralleling of CTs of strong fault sources with weak fault sources. Okay, and CT and paralleling of CTs should be done very carefully. CT paralleling, sorry. Okay. Okay, so now the basic idea is that current through the restraint coils should be in phase, and I mean, in addition to that, there should be, and rather I'll put it a little differently, and for external faults and overloads, the operating current or the differential current should be minimum. Okay. Now, it is actually done in 2 steps. Okay, we will see that. One is of course phasing. Now, phasing means you could have a phase shift across the transformer because of the different vector groups. So, to this can be done by using star delta CTs or Y delta as if as may be preferred. And the second is ratio adjustment. Okay, there could be we will see this by an example. This can be done using CT taps or relay taps or both of them together, okay, depending on what range you want, or both, to minimize current flowing in operating winding. Now, let us see an example of a power transformer, say an 100 MVA delta star transformer with a primary rating 220 by say as a secondary is 110 kV. Typical, we are just taking an example, but this is like a typical rating, a fairly large transformer which needs to be protected using differential protection. So, how will we do this, we will take care of phasing, and see, we will just draw it so that it is say easier to understand. The first element will be a breaker. So, I mean just a representative, you could have you could skip the breaker, but then the differential will have to include the incoming cable and all that. So, there are nuances there. We will not get let me leave some space, because there will be some space needed for drawing. So, okay, so this is the 52. 52, if you remember, the IEEE device unit number is for a circuit breaker. Okay, so this is the A winding. So, this is A, high voltage side, A, B, C. So, this is the A phase winding. This is the, we will connect it. This is the B phase winding. Sorry, just improve the drawing. And this is the C phase winding. We will connect it in delta by connecting this to this, this side to this side. We will just show it by and this the remaining winding here. Okay. So, the current flowing here will be say this is I, this is IB, this is IC. So, I minus IB, IB minus IC in this phase, and IC, because this is a delta, IC minus I. Okay. So, similarly on this side, because it is just the circuit breaker which is in series. Now, we have the CT. We will see the connections just very shortly. We will just draw the CTs and then connect them later. Okay, so, the same dot convention as earlier, entering, leaving. Now, we will draw the secondary of this transformer. This is 220 by 110 kV, and these are the secondary is in star. Okay, this is just an example we are taking. So, this is typically earthed. So, we have A, B, C and A, B, C. So, I just draw this. This is the same circuit breaker, but I am just drawing it in a bit more compact fashion, because I did not realize that we will need space for the CT connections also. So, this is 52. They are the same circuit breaker. Don't it is just my drawing that is a bit okay. So, now in the what we have here is we have we will have if we connect these in star, okay, and this, since this is the common we will have to have a common connection here also. Since we will, if these are in star, then we will have IA minus IB, IB minus IC and IC minus IA in these also. So, in the operating coils of these also. Here what, on the other hand, we have IA, IB and IC, because these are in star. This the primary the transformer, the main transformer windings are in star. Okay, so, from in these transformers we will have IA, IB and IC. Here we have got IB minus IA minus IC. This is IA minus IC, this is IB minus IC, and this is IC minus IA. So, this we will have to connect in star. Okay. So that the I think I will just take this down and okay, then just not drawn it, make it a little more convenient. Okay, so these are the two restraint windings, and this is the operating winding for the A phase. Okay, so now this, since this is IA minus IB, this side of this side, that is this side, I will just rub this out, but this side will have to mean, because otherwise you will get only IA, IB and IC. So, to avoid that, we will have to connect this side CT in delta. Now, this is what all that I am discussing is true for, because we are discussing with the legacy system, but is true for electromechanical relays for sure. You can do this in numerical relays, or you can do this addition or subtraction IB minus IC inside the numerical relay also, but it has to be programmed properly. Okay. So, now this will have to be connected in delta as, oops, the rubber is on. To make it IB minus IC, we will have to connect it, IA minus IB. Oh, just a minute. There isn't enough space. Okay. Similarly, this will IB minus IC, and finally IC minus I. These are the dots that I have IC minus I for IB, this is for IB minus IC. Okay. Oh, the third one is here. Okay, and then we will have the restraint winding. So, the operating and restraint winding. So, what have we done here? The HV windings have IA minus IC, I am sorry, IA minus IB, IB minus IC, and IC minus IA currents. Okay, flowing through, this is flowing here. Okay, and so these CTs will, since these are in star, they will carry the same current with the polarity as shown, because this this is flowing like this. So, here in these CTs, this will flow in the opposite direction. Okay. So, these will then flow in the restraint windings also. Now, to get what we have done is to get IA minus IB here also, we will have to connect these CTs in delta. Okay. So, though this transformer winding was in star, now we have connected these CTs in delta to compensate, to get the same currents flowing in the same restraint windings. Okay. So, since they have to flow back through the star side. Okay. So, now this is how phasing is handled in general. Okay. I have shown it with an example how a phasing is handled. So, if you have a star delta transformer, then what you will do is, on the delta side the CTs will be connected in star, and on the star side the CTs will be connected in delta. Sometimes it may not be possible to get these main CTs in star and delta. Then what if you have a delta star CT here also, then you use what is known as a auxiliary CT or an interposing CT, as it is known as, okay, which is then itself a star delta. So that eventually you in the the idea is that in the restraint winding you should have the same currents flowing. So you have IB minus IC here, you need IB minus IC here. Okay, so you can do it with the main CT is connected in delta, or then you have an interposing CT and do it. So IC minus IA, I am sorry, IC minus I and IC minus IA, IC minus IA here also. Okay, so now the final thing that is left is the tap selection. Okay, so CT ratio and tap selection. So let us say that this is as this is 100 MVA to 100 MVA 220 by 110 MVA 220 by 110 kV transformer. The ratio error or the percentage error is given by, say, IH is the high voltage winding current, IL is a low voltage winding current, then TH is the tap or relay tap on the high voltage side, and TL is the relay tap on the low voltage side. Then this ratio error is given by this formula, where S is smaller of the two ratios. Now what is IH? 100 MVA divided by root 3 into 220 kV. So this gives me say 262 point, I just worked it out, 262.43 amperes. So since it is 262.43 amperes and we want to select a CT with ratio as close to this, including 10% overlap and all that, let us choose a 300 by 5 CT. Okay. So IH, that is the current on the secondary side, will be 4.373 amperes. Okay. IL on the other hand will be how much? 1000 by root 3 into 110 is twice of this current, so it will be 524.86 amperes. So this is let us choose a 600 by 5 CT, same logic, and IL will be the same. This is IH is nothing but 262.43 into 5 by 300. Okay. So divided by 60. Okay, and IL will be the same. So 524.86 into 5 by 600. So it will give me 4.373 amperes. But this is in the CT secondary. But because of the CT connection in the restraint, what will we have? We will have IR is equal to, here this is the same as the I restraint. Okay, I or I restraint dash, if I were to call it in the and I restraint dash will be, the double dash will be into root 3. Okay, so 775 amperes. Okay, so now in this particular relay, say TH is, we take TH as 5 and TL as 9. So TH by TL is 0.5 56 and IH by IL is 1 by root 3 is 0.577. So our M we will have to we can calculate as 100 into IH by IL minus TH by TL 556 divided by 0.556, we will get something like 3.78% or so. So all the differential relays that we said, transformer differential are generally variable percentage bias differential with differential of 15 to 60% can take care of this. So, so that's how the two steps for relay setting are done. First is the phasing and second is the tap selection. So in the relay tap, you will choose 5 for, depending on this, you will choose 5 for the high voltage side tap and 9 for the low voltage side tap. Okay, so this is how the relay setting for differential relay for this 100 MVA transformer is done.